Hi, and welcome to the second part of your power series video where we're going to be differentiating and integrating these power series. So the sum of a power series is a function, right, of this. Here's my summation notation. And we can find the derivatives and integrate these series using this theorem. And I'm going to sort of just show you what this theorem looks like, but then I want to get into how to use it because I think you're going to find this to be very intuitive. Because these are power series, we have nothing but powers of x, or x minus a, for example. So we are going to be using the power rule for differentiation and for integration. It's basically what it says. Okay? So let's look at one example here. If your function is this infinite series, find the first four terms of f prime of x and write this power series for f prime of x. Okay, great. Well, what I want to look at is, first of all, what are the first four or five terms for f? Okay, so let's just write out the first four or five terms for f. So if n starts at 1, my first term is going to be positive, and this will be x to the first over 1. And then minus, because when n is 2, this is going to be negative. And when n is 2, this will be 8 minus 3, so x to the fifth over 5. And then when n is 3, this will be positive, and that will be 12 minus 3, so 9 over 9. And then when n is 4, this will indeed be negative. 16 minus 3 is 13 over 13. I'll put plus dot 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 because in case I need to find another term. Now, when I take the derivative of x, I do get a value. So since I'm asking for the first four terms of f prime, I should be fine with just four terms in f. I'll show you what I mean. If I just wanted to write the first four terms of f prime, I could do it right from here. I know the derivative of x is 1, right? Because you can differentiate term by term. You've been doing this all along for all of your polynomials. Now this is just an infinite polynomial. Well, I'm only asking for the first four terms, so I don't need all of them. I just need four of them. Now I'm going to do power rule on x to the fifth over 5. So when I bring the 5 down and multiply, that will divide. So this derivative should just be x to the fourth. Do the derivative of x to the ninth over 9. It shouldn't take you too long to figure out that's x to the eighth, right? Bring down the 9 and multiply. Those will divide. 9 divided by 9 is 1, and I just get x to the eighth. And then minus x to the 12th. Again, it only wanted the first four terms of f prime of x, and I've got them. Okay, so here's the first four terms of f prime. Now, if I take that infinite series, I could have done it from here as well. So if I've got the summation notation, got negative 1 to the n plus 1, x to the 4n minus 3 all over the quantity 4n minus 3. And I'm going to write in front of this something that you might not have been putting in front of any of your power series in the past, is that this is equal to f of x. Okay, so in this case, I want to find f prime of x. So that means n is 1 and then 2 and then 3 and then 4, etc. N is not necessarily what I would call my variable. I am not doing the power rule on n. I am differentiating with respect to x. So it is still an infinite sum from 1 to infinity. My negative 1 to the n plus 1 should not change because that is a constant value, either negative 1 or positive 1. My derivative won't change that. But I am doing the power rule on x to the 4n minus 3. So how I do a derivative using power rule is that exponent comes down and gets multiplied. Keep your base the same. My base is x. And I subtract 1 from my exponent. So that gives me 4n minus 4. And this is all over 4n minus 3. And now you should see that the 4n minus 3 quantities divide to 1. So as a series, I can look at this and say it's from n equals 1 to infinity of -1 to the n plus 1 times x to the 4n minus 4. And I would just double check to make sure. Sometimes when you take the derivative, for example, if I take the derivative of 5, it's 0. And I don't necessarily write 0 plus. And so my whole series seems to get shifted over one term. And so I do want to just double check to make sure that that series notation, okay, that this series notation will get me the 4 terms that I know it should. And so if I put n equals 1 in, this does start positive, so that's good. And if I put 1 into my exponent for n, so 4 minus 4, it would be x to the 0. That's 1. And so I can check each of those 4 terms, n equals 1, n equals 2, 3, and 4, and they all work out fine. So differentiating and integrating shouldn't be a problem at all because you're just doing power rule. All right, so because of that, I can take a series that I know and I can use that series to either take the derivative of that series or the antiderivative of that series to come up with a new one. So we always talk about creating a new series from an old one. I can do that through derivatives or antiderivatives as well. So I want to express 1 over the quantity 1 minus x, that quantity squared, as a power series by differentiating this known series. So again, here's my known or old series, and I want to see how I can use that one to get the new one. Okay. Well, it says by differentiating, so I'm just going to kind of prove it here. So if this is my f, then f prime, I'm going to use chain rule here. So I brought down my -1, keep your base the same. Now it's to the -2 because I subtracted 1 from my exponent times the derivative of what's inside. And so f prime of x is in fact that derivative. So if I know this series, so here's my known series that I'm working with, I can take the derivative of that to come out with this new series. Okay, so I can say 1 over the quantity 1 minus x squared is, well, the derivative of 1 is 0, and this is what I was talking about us needing to be careful with our terms now. Derivative of x is 1, derivative of x squared is 2x, and I can keep going, but here's what this is going to look like. If I take the derivative of x to the n, it truly should be n times x to the n minus 1. Well, let's make sure that this actually works. So if n equals 0 is my first term, and see, we don't usually write 0 plus in my series. I would normally just say the series is 1 plus 2x, and this being x cubed, its derivative would be 3x squared plus dot dot dot. So I want to get 1 as a first term. So if n equals 0, do I get 1 as a first term? And that answer is no, because I would get 0 times x to the -1 or 0 over x. So I don't get 1 as a first term when n equals 0. So I have a couple of choices. Now, if your summation is already started for you and it is insisting that you start at n equals 0, then what you have to do is adapt your n's in your actual formula. So if I want to start at 0, I can just shift the series to the right or adding 1 for n. And so it would look something like so. If I put in n plus 1 instead of n, because again, I got rid of this 0 here, so I'm really shifting this series over 1 to the right because I don't want to get the 0 as a first term. I want to get the 1 as a first term. So the next term idea was putting in n plus 1 instead of n. So I could say this is my series. Or if you get to choose, there's nothing wrong with just changing your starting n value. and saying, okay, I can start at n equals 1. And by starting at n equals 1, I think I will have fixed my issue here. If I start at n equals 1, then I can leave n times x to the n minus 1, because that'll be 1 times x to the 0. And so it's just a matter of, what do you want to change? Do you want to change your starting value for n, or do you want to change your pattern or formula for your summation or your power series or just your series in general? But either one are equivalent. It just depends on how you want to write it. You just have to make sure that when you plug in your first n value, that you get the first term that you want. All right, so let's look at this other example here. And we just have a few more to look at. So if we are trying to find a power series representation for natural log of 1 plus x, I recognize that I gave you one on your paper for the Maclaurin series, but the derivative of natural log of 1 plus x is 1 over 1 plus x. So since we know the series for 1 over 1 plus x, we can anti-differentiate that series with respect to x, and we will end up with the natural log series that we want. Don't forget your plus c when you anti-derive, even with the series. So here's my known series. Known series for 1 over 1 plus x. This is my known series for 1 over 1 plus x. Here is my known series for 1 over 1 plus x. And I want to anti-differentiate that. Again, you're doing nothing more than power rule. So the antiderivative of 1 is x. The antiderivative of x is x squared over 2, and so forth. Here are my antiderivatives. You can do the same thing in the series notation, okay? So I can take my negative 1 to the n is going to stay negative 1 to the n, because that is not dependent on our x, and I'm anti-differentiating with respect to x. So I added 1 to that exponent, so n plus 1, and divide by n plus 1. And then all I need to do is check to make sure that those first terms match. Again, don't forget your plus c. And so because we don't want our plus c to look like it's in that sigma notation, oftentimes people will start their series with c plus, so that you make sure you know it is not inside of your summation or your series formula. Otherwise, you're adding it on n times, right? So if n is 0 and I want to start at n equals 0, I get negative 1 to the 0, so that is positive 1. X to the 0 plus 1 would be x to the first over 0 plus 1 is 1. And that is in fact my first term, so I don't need to make any sort of adjustments here. So why do you ask, do I have an or situation? Well, that's just kind of a tricky thing here. Because you see so many n plus 1s, oftentimes people just like to deal with x to the n better. And so what they do is shift your series so that instead of talking about n plus 1, which n plus 1 is a next term idea, they'll just go to the next term. So they'll just use n equals 1 instead of that n equals 0. That's entirely up to you. That might be a little bit more advanced as we start getting into these series. You might decide you like the look of them one way or the other, but just knowing that you have different ways of writing these series out, which was also discussed in a previous video here, is very, very helpful. And that radius of convergence is still 1 because I'm still just dealing with x to the n. Okay. So let's talk about integrating a little bit more here. So let's use a power series to integrate the following. I want to integrate x squared natural log of the quantity 1 plus x dx. And I can do this by turning this into an infinite power series and then integrating that series. And so what we're going to end up with in the end when we do more of these and have a few more, well actually in the very next one, is we're going to use this power series to approximate a definite integral. And so I'll put bounds on the next one. All right, so here is a known series for natural log of the quantity 1 plus x. Okay, so I'm going to start with that. Now, I didn't change natural log of 1 plus x. That is exactly what it looks like. But I want the series for x squared times natural log of 1 plus x. So I have reasons for this. I'm going to actually write out the list of, I'm just going to use 4 terms here. Again, when we do a definite integral, that's going to become important. So I'll multiply or distribute in x squared. So this will become x cubed. If I multiply x squared by x squared, I get x to the 4th over 2 plus x to the 5th over 3 minus x to the 6th over 4, dot, dot, dot. And if I, in my summation notation here, think about if I multiply this by x squared with the same base, we add our exponents. So nothing else should change other than it should become x to the n plus 2. And again, you should stop along the way and just check your power series before you differentiate or integrate. Do you get the terms that you think? So if you put in n equals 1, do you get this first term of x cubed? And just make sure that in fact you do. All right, so now I want to integrate this series with respect to x. And again, I'm going to write out 4 of these terms because I think it will be helpful for you. So if I integrate x cubed, I get x to the 4th over 4. If I integrate x to the 4th over 2, I get minus x to the 5th over 5 times 2, which is 10. If I integrate x to the 5th over 3, I get x to the 6th over 6 times 3, which is 18. And the last term that I'm writing out here would be x to the 7th over 7 times 4, or 28, plus dot, dot, dot. And I will integrate this series. So again, I'm not looking and trying to reinvent the wheel or recreate the wheel here. I'm not looking at this and trying to create a pattern from scratch. I'm just going to integrate the pattern that I have here written in yellow. So nothing should have happened, or so I think, to my positive and negative alternating terms, although sometimes I have to shift things over one because I either lose a term or gain a term. But this x, I am doing an antiderivative with respect to x. So here's where my power rule is going to occur. So my base stays the same. I add 1 to my exponent, so now it becomes n plus 3, and I divide by that same quantity, and I had an n already down there. And that's it. There's my new power series. I just want to make sure, and I need to put a plus c in front. And again, most people put this c plus in front of their summation because there could be some constant of integration there. And so if n equals 1, am I getting my first term, which my first term is x to the 4th over 4. So if n is 1, that would be negative 1 to the 0, so that works for me. And if n is 1, I get x to the 4th over, n is 1, that would be 4 times 1. So it should be x to the 4th over 4. That's exactly what I have. So there's my power series. So let's do that again, but with a definite integral so that you can see how this works to approximate this. So we're going to use this power series, and we're going to try to figure out what this antiderivative is, and we're going to be accurate to 6 decimal places. Now it sounds like you're going to have to go out to a ton of terms if you want 6 decimal places, but most oftentimes these values get really small really fast, and so typically we're only working within, I would say 4 to 6 terms, but you can certainly write out more if you're unsure. You also should, by all means, put this in FNINT to get an accurate estimate of where approximately we should be. And when we use function integrate on our calculator, we're approximately 0.000983. So I already know where I want to end up. Now, arctangent of 3x. I am starting with the arctangent of x, or inverse tangent of x series that we know, and I substituted in 3x in place of the x. Okay, so I can write that out. 3x minus, this will be 27 over 3. So this will be 9x cubed plus, this will be 243 over 5, x to the 5th. And this will be, I don't know, we're going to call it 2187, x to the 7th over 7. You could have said 3 to the 7th. That is fine. And then if I wanted this term, I could say plus 3 to the 9th. And I know that will reduce with 9, but that's okay. X to the 9th minus da 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 da. Okay. And I haven't really changed my summation notation, but all I have done is say that I'm going to separate this out. So it's going to be negative 1 to the n times 3 to the 2n plus 1 times x to the 2n plus 1. I just separated my constant from my x. In other words, I removed the necessity of the parentheses. You'll notice in the blue, I still have that quantity 3x to the 3rd, the quantity 3x to the 5th, but in the red, I just have x to the 5th. So it's making my power rule so that I never have to use chain rule or use substitution to find that derivative or antiderivative. Okay, so I like the x's to be separate. Well, my series that I'm trying to write isn't just inverse tangent of 3x, it's x times inverse tangent of 3x. So I have to take this series and multiply by x. Now, whether you write inverse tangent or arctangent, we're fine. So if I distribute the x, this would be 3x squared minus 9x to the 4th plus 243 over 5x to the 6th minus 2187 over 7x to the 8th plus 3 to the 9th over 9x to the 10th, da, 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 da. And my summation notation would be still negative 1 to the n. I still have the same constant for 3, right? It's 3 to the 2n plus 1. But now when I distribute it in an x, or think about if I multiply in an x, it's really x to the 1st. So you add those exponents. So you do get 2n plus 2. So this is what my series will look like. Now, if I just had to anti-differentiate this with respect to x, I'm anti-differentiating this whole thing here with respect to x, and I can anti-differentiate my summation notation with respect to x. If I didn't have bounds, I would probably just want to do it from that sigma notation. But since I'm trying to evaluate this indefinite integral, I'm going to want to work with those individual terms that I wrote down. And since I'm going from 0 to 0.1 that was given in the beginning, I want to integrate this and then shove in my bounds from the individual terms, not from that sigma notation. So if I integrate this, I get 3, and then it's x cubed over 3. Again, I'm just doing power rule. Minus 9/5 x to the 5th plus 243 x to the 7th over 35, and then minus 2187 over, this will be x to the 9th, so it'll be over 63. And then I don't know how many terms I need. I can always go back and find more if I need more. And I'm evaluating this from 0 to 0.1. So I really only have to evaluate this at 0.1 because if you put zeros into any of these terms, you're going to get 0 for each term. So I'm going to put in 0.1. So this will just become 0.1 cubed minus 9/5 times 0.1 to the 5th plus 243 over 35.1 to the 7th minus 2,187 over 63.1 to the 9th. And I haven't even begun to see if that, reduces. It doesn't matter. Okay, and then I do have minus 0, plus 0, minus 0, dot, dot, dot. Okay, once I substitute in that 0. So now I need my calculator to help me evaluate what these decimals are going to be. So I'll get that out and let's see what we can do here. So I will say what is, and I'm just going to type this in exactly how I see it. So I'll do it over here. Okay, and here's what that looks like. So I do each individual term on its own. And so my 0.1 cubed, the cubed is off the screen there, is 0.001, which I'm guessing we probably already knew. Okay. And then I go to my next term, that's the 9/5 times 0.1 to the 5th, and that's 1.8 e negative 5. So that will become minus, because of the minus right there, 0.123418. And so if we look back at this just to make sure here, yep, e negative 5, so that's times 10 to the negative 5th. So I should have 1, 2, 3, 4 zeros, followed by that 1/8. Now in this next one, it's going to be 0.1 to the 7th. So I'm going to move this decimal place over 7 places. So there's going to be 6 zeros followed by, I'll just write down 694. So plus 6 zeros, 3, 4, 5, 6. And keep in mind, you want it to be accurate to 6 decimal places. 1, 2, 3, 4, 5, 6. So I look at that 6 decimal place. This 6 does round and make that a 1. And so it will change the value of my 6 decimal place. So I just check the next term here and see what that was on my calculator. So that was this 0.1 to the 9th times 2,187 over 63. So that's e negative 8. So that's going to be this 3.47 number times 10 to the negative 8. So I'm going to move this decimal 8 places to the left. So there are 7 zeros and then a 3. So 1, 2, 3, 4, 5, 6. So this is definitely not rounding enough to affect that 6 decimal place. So I do not need that term. And so if I just add these 3 numbers up, just those 3 terms, so there I added up the 3 terms. Obviously the second one's negative, but I get 9.826 times 10 to the negative 4. So this is going to be 0.0009826 or 0.983. Since this was a 2/6, I would round that to a 3. And when we used the function integrate from the beginning, we saw the exact same value there. So you should be able to integrate just about anything that you can turn into an infinite series and approximate to whatever level of desired accuracy you want. And this is actually how your calculator behind the scenes is doing some of these trickier integrals, is it's transferring them into these series and then integrating from there. And so this should take you through your power series and how to create a new series from an old one, whether you are just rewriting the series or differentiating it or integrating it. And the very last thing we'll do in this course is use, or in this sort of chapter, if you will, is how to write your own series. So how to come up with a Taylor polynomial, or what is a Taylor series or Maclaurin series using its definition. And that will take us through that, and I hope you found this helpful.